Lovely. So first of all, thank you again for giving me the opportunity to talk about this fun piece of work. So I'm Jordan. I'm a final year PhD student at Queen Mary under Juan. He's my supervisor, and this was work with Greg Taujanskas at Cambridge. So whenever I give this talk, I like to say my title is long and convoluted, but by the end, hopefully you understand what it means, and kind of some of the techniques that I talk about. Just one quick question. Can everyone see my mouse moving around on the screen? Or no?
Yes, yes, we
Lovely.
can.
Okay, good. That way I can point. Okay, but here's the rough outline for the talk. I'm going to give some motivation, some of the geometric setup that's in the problem, and how we actually phrase the problem. I'll talk about some main results and maybe a little bit about the sketch of the proof. Some of the technical details aren't so important, but I think it's good to have an idea of where they come from, and some future directions and stuff that I'm working on now. So let's go. So first things first, this is one of my first projects that I actually worked on and put a preprint out for this in August. And the motivation is my supervisor told me to. I think this is normally how I lead. Or it's Greg, he said, please follow on from our previous work. And I said, well, this is nice, but what can I do in this to extend the work and to extend to this case, which doesn't quite neatly fit in with the general spin paper that they did previous. So I looked at the literature and went through. So the way that I understand the nature of these conformal scattering problems is you can look at it in the following. So it's the 1960s, and Lex and Phillips have some scattering theory, particle interactions, and that uses some pretty formal methods, at least at the level of function spaces. And then, a few years later, Penrose introduces the compactification of non-compact pseudo-Riemannian manifolds into a compact manifold boundary describing infinity, something that I think most people in the audience are familiar with. So apologies if this is slightly boring. But then, you fast forward 20 years, and what happens is that Friedlander comes along and kind of combines these very independent notions together. And this is kind of what we would look at more, I guess, towards today as like a conformal scattering theory. So once you have now the conformal boundary available, it raises, I think, a natural question. It's how the past and future asymptotic data of massless fields, how they're related to one another. The massless part so that you can actually reach your boundary, and the past and future part is hopefully quite clear, at least in the context of I have some in-states, some interaction will happen, and you want to describe some out-states. At least at the particle level, that's what it looks like. For like something like radiation, you've got something coming from the ancient past and will live in your bulk for some time, and then it will escape to a future where we can do some detections or figure some things out about the thing we're studying. So, of course, that in our case, we want to take something which is asymptotically flat. So that means that the conformal boundary is actually a null hypersurface. So this is the standard problem. So then really what conformal scattering looks like in this particular case is a characteristic initial value problem with data given on the conformal boundary. So because I'll be talking about the wave equation later, I thought I should give this image now, and I think it's quite useful to look at. So in particular, this is, of course, Minkowski. This is where where the analysis will be happening. So of course, you've got scry as the null hypersurface at the boundary. And what we will show is that the domain of interest is this thin rectangle along scry. So we'll be prescribing some data, which is characteristic, so on scry and on the short incoming null hypersurface. And we'll determine some property about the solution to the wave equation at future null infinity in this neighborhood of spatial infinity. So this is really a thin rectangle. This is the picture you should keep in your mind. Oh, and I should say, if there's any questions midway, just feel free to interrupt me. It's my first time giving a talk online, so. All right, so if we want to refine our question earlier now with at least this picture in our minds, it's really the question of how the gravitational radiation of physical objects and regularity at the past conformal boundary affect the structure of solutions. towards the future. That's a slightly more precise way. So how can you see this? Well, one answer is that there's polyhomogeneous behavior towards square plus. Okay, so what does that mean? It means that if I give you some kind of boundary defining function for the manifold, so at the boundary, you want this function, which is non-negative, to actually vanish there. Polyhomogeneity is saying that when I expand my solutions towards the boundary, I get terms which look like powers of the conformal factor in this particular case, and logarithmic terms thereof. This has been seen in lots of different contexts, and every time someone wants to write a list about why you might get behavior looks like this, the list of literature is always varying. But I think as early as Friedrich, Grigalius, and lots of other stability results of Minkowski look at this and get slightly different asymptotic behavior. But this is something which is hopefully well known by now. And of course, why does this crop up? It's, Einstein's equations are very nonlinear, and they're partially responsible for this. But there's another thing too. There's something which can survive at the linear level as to why you get behavior which is not quite smooth. And this is where you have the problem of spatial infinity, right? So here, this is where precisely where we saw this corner in Minkowski, where the generators of future null infinity and past null infinity intersect, and they really degenerate there. So if you really want to study the wave equation as a characteristic initial value problem with data on the past, then you actually need a better representation of spatial infinity. So again, if we're looking at our domain, and I'm prescribing data here on these null hypersurfaces in orange, right? I have some existence theorems which tell you that you can get a solution in here. But what you really want to know is what happens right in this neighborhood. And because of this degeneracy, this causes a couple of problems. Okay, so this is something which is shown that can survive at the linear level. So here we'll be using Friedrich cylinder spatial infinity. So you're going to blow up now spatial infinity instead of this really degenerate place. You're going to expand and use some kind of geometric blow up. And in particular, I guess the topology goes like a interval cross S2. And in particular, what does that mean? In Minkowski, you can get away with it without such a nice description using conformal geodesics by looking at some kind of ad hoc coordinate transformation. So if T and R are your physical coordinates on Minkowski, then you can define new coordinates rho and tau in the following way. And in particular, what this means is that tau will be ranging between -1 and 1. And at -1, this is saying that I'm at the past conformal boundary. And at +1, I'm at the future. And rho is like an almost an inverted radial coordinate, if you like. When rho is 0, that means I'm at spatial infinity. So I guess this is this coordinate axis here. And for rho positive, you're moving away from spatial infinity or the cylinder. And in particular, this omega that I was talking about before. Let's probably hide this. So this omega that I was talking about before, this boundary defining function, or the conformal factor in this case, it splits like this, and this is just simply 1 over r. So this geometric blow up together with this change of coordinates, if you like, is what we call the F gauge. And maybe one comment about this. This is non-unique, right? This way that you can perform some kind of geometric blow up. I guess just because of the history, this is the one that we're using, but you could have looked at many others. There's also the Ashoka-Hansen hyperboloid, and more recently, and in the past as well, there's other geometric blowups using like radial compactification from like the school of Marajh. So this is just historically what we're using. Okay, so let's just quickly state what the main theorem looks like. So here's a rough version. So if I want solutions to the wave equation, there's spatial infinity on Minkowski, then what I can do is I can tell you that there's sufficiently regular asymptotic characteristic initial data, so like on those orange hypersurfaces that I showed at the past, And what you can do is you can show that there's a solution in the development, and in particular, future null infinity, which has suitably regular asymptotics in a neighborhood of spatial infinity. Now, what's the point is that I'm being very vague here about what it means to be sufficiently regular and suitably regular. This is something we'll pin down a bit more later. But in particular, I want to say that we're talking about nice solutions in a sense, slightly different to this polyhomogeneous stuff. But we'll kind of see why things don't work out in this way. Okay, so what you want to do a bit more concretely is recast the wave equation on Minkowski. So here it is. I'm using tildes for things on physical space. And you can rewrite it as a symmetric hyperbolic system. So you can use some nice existence results from Cato with this nice textbook, and existence results which have come up in a couple of places for the characteristic initial value problem. So there's this work in the 90s by Rendell and Luke in 2012, and an extension in 2015. And there's another reason. If you ever want what you have here and Minkowski to be useful in the non-linear setting, then what's the point is you want to now transport this to Friedrich setup where you've got the conformal field equations. So this is almost a precursor in the tools that you should be familiar with. Okay, so what does the wave equation look like in the F gauge? So now dropping the tildes, so we rescaled phi, it looks something like this. So you can see the degeneracies that we were talking about at spatial infinity are a little bit more precise. So what happens is that when tau goes to plus or minus 1, this leading term on the wave equation vanishes, right? And then this is where you introduce some kind of degeneracy. But if rho is positive and tau is plus or minus 1, so I'm at future null infinity, but not necessarily at spatial infinity. This is just like some kind of coordinate degeneracy or singularity, if you like. But when rho is 0 and tau is plus or minus 1, that's when you have an actual issue in terms of the principal symbol when you decompose to check hyperbolicity. So that's one of the reasons that this thing still fails even at the linear level. One of the reasons it carries over. This is also something that you see, not just for the wave equation, but for fields of arbitrary spin. Okay, so how can I do this rewriting of the wave equation in a symmetric hyperbolic system? You can define new variables. So this psi, and then psi 0, psi 1, and psi 2 in this way as a combination of derivatives of your original field. So, casting our minds back to like the standard PDE class, defining one variable to be the time derivative of your initial one seems very natural, but then where do the others come from? So there is a really lovely blue textbook that most people are probably very familiar with. So in Juan's textbook, he actually has a way that you can write using some nice things about spinners. So some kind of spin diode will be introduced as a way to actually write down these components and exactly how they fall out. So in essence, what's happening is I'm sweeping some stuff under the rug here as to how you go from here to here. But it's, if you like spinners, this is actually where things would come into play. So what's nice is that a symmetric hyperbolic system almost falls out for free by considering, okay, I can define one variable to be the derivative of the other, like so, for this psi. And then you would use an evolution equation, which comes from that, like some kind of like Bianchi identity in a sense. For like the conformal field equations, there's an analogous statement as to how you can write that down for here. And then these psi 0, psi 1, psi 2 come from contractions with a spin diode. Okay. And maybe just one small comment as well, if people aren't familiar with some of the precise things which are happening. So this x minus and this x plus, you should just think about them as combinations of like spherical derivatives. This way, there's something else happening here, but you should just think about them as combinations of those derivatives. So you can use these variables along with phi to rewrite the entire thing as a system and exploit some existing results for existence, stuff like this. Okay. Let's move on. So once you actually have these conserved quantities, once you have these variables, you can write down conserved quantities from the system, and that's where things get maybe either nasty or you see some of the beauty for the setup. Okay, these red boxes are to remind myself to see if I've forgotten anything. I've spoken about degeneracy, so that's fine. And I've spoken about where these come from. Good, okay. So the symmetric hyperbolic system, you write this down in terms of those auxiliary variables that we defined, the phi and the size, and the equations, or a linear combination of the equations that you get. They look something like this. So I've displayed them. They don't look incredibly intuitive, maybe at this level, but there are some things that I would like to point out in relation to some previous work. So Friedrich in 2002 had this nice paper about spin-2 fields near spatial infinity. And then the structure of these equations is analogous to that you would find there. Actually, I think it's 2003. But the structure of the equations is similar to that you would find there. And this is really what Juan and Greg really looked at and saw, we can exploit this recurring behavior and extend this. But now the reason that the wave equation wasn't included in this previous paper is because there's this mixing of different variables. So for fields with spin, you can do a similar process and compute these auxiliary variables, but there will be a couple more of them, let's say. But what happens here is that you've got a mixing between, if you take a look at B0, this equation, you've got a derivative operator acting on psi1, so it looks like 1 minus tau partial tau plus rho partial rho on psi1. And in the same equation, you've got something acting on psi, and a similar thing in A1. Now, because of this mixing, it looks like a double transport equation almost. And that's actually where some of the slightly messy things come in. And the standard conserved quantities that you could write down from these equations actually become messy and don't follow the same structure. However, not all is lost. Because when you do want to find these conserved quantities, you can use, your favorite thing that you'd like for doing this. Some people prefer a more geometric method. But if you're a fan of Mathematica, then commuting for these higher order currents is actually fairly nice. So here are what the conserved currents look like, at least structurally. I can apply this operator D, which contains rho derivatives, tau derivatives, and these x's. They're made of these functions z. You can construct these from the lifting, technically speaking, of your S2 to S3 to avoid some coordinate singularities, but that's just a technical thing. But you can think about them like rotational vector fields. So if you if you hit this onto A0, B0, A1, and B1, and you multiply by the appropriate combination of psi k and psi, you'll have the following higher order currents. Now, what's known was the first one, things should look like, or structurally look like, this, without this last term. This kind of clean behavior is why doing it for higher spin was almost systematic. But because due to this mixing of the components of the field, that's why you not only have this extra term, but also in the second, a different sign. This is technical, but it's just to see that structurally they don't behave exactly the same. That's why it doesn't fall into a nice hierarchy. Okay, but then what you can do is you can actually work with these currents, and you basically just want to do the divergence theorem to then prove some estimates. Okay, so before I actually show you anything about how these things decompose these currents, let's take a look at how the geometry changes. So remember, this was the Minkowski diagram for the domain that we're considering. Sorry, the Penrose diagram for Minkowski for the domain we're considering. And then the question is, how does this look like in the F-gauge? Now, I'll put a picture up here. So the entire region with these almost, it looks like curved lines. This is just a coordinate diagram on the right. This entire region is what D transforms as. So this B epsilon here is precisely this one here. This B1 would be the top line, and you can see where spatial infinity has been blown up on the right-hand side. There's a couple of things to say about this, is that this is effectively a visual way of understanding how the proof works. You've got a large upper domain where I believe Friedrich started with from a T or a tau equals 0 hypersurface and proved estimates for spin 2 up to future null infinity by showing some estimates which are independent of the foliation parameter. That's the idea which you can extend to, of course, Cauchy surfaces which are not T equals 0. So you can drop it as low as you like, but fix some epsilon greater than 0 so that you don't actually touch past null infinity. And then you treat the problem in a slightly different way in the bottom half. But that just means you have to use a more refined version of the F-gauge, where these lines are not necessarily horizontal for future null infinity and past null infinity, just so that the existence theorems actually work. Okay, but again, this is slightly technical. What's the takeaway is that you can see how this transforms, and there's some notation that we'll get used to. So just to say this in a slightly more concrete way now, if I fix this cut of past null infinity by fixing some epsilon greater than 0 and a value of rho, which is positive, so you're not sitting on the cylinder, then you can talk about regularity there. So if I give you data on the past conformal boundary on a short incoming null hypersurface as well, that is sufficiently regular, then the wave equation admits a unique solution at future null infinity, which looks like a nice Taylor expansion. So here you've got some remainder in like a Holder space, and the field expands. You can expand around rho, so around the cylinder, up to some particular order that's kind of restrained by the data that you give. And this expansion is valid. That's precisely the point. You're not assuming anything about the expansion at the future. You can actually prove that such an expansion exists from given data. So one thing to say is that the coefficients in the expansion, the tau dependence of them, you can compute them explicitly using Jacobi ODEs. So there's this nice old textbook by Sego from 78. And that's where you can take a look at the equations which you get when you're restricted to the cylinder. Those ODEs and the solution of those ODEs are very well studied. And you can actually see where logarithms may appear in terms of the coefficients, the equations for the coefficients that you write down. Okay, but there's a slightly more horrendous technical version with lots and lots of derivatives on it. So I've been vague about what I mean by sufficiently regular. This is the only time I will show you this for honesty. And that's just because it does look quite technical. But I think it's important to understand why you might have so many derivatives. So again, cast your mind back to the Minkowski diagram, so the Penrose diagram, where you're given data on this characteristic, hypersurfaces. So if I give data for the wave equation, what that really means is, because I've written it as a symmetric hyperbolic system, I have to give data for all of the components. So what does that mean? It means that I need to specify how much regularity each of them needs to have, and it just says I need to have a fair amount for m plus 23 if you want your expansion to be valid up to some order n. And these are just transverse derivatives on past null infinity or the short null hypersurface. And in particular, what you can do is instead of prescribing all of these different values, you can actually effectively compute them from the radiation field and the one coming from the short incoming null hypersurface by studying the equations on each of those. So in fact, you would only have to prescribe this at square minus, this along B epsilon, and the initial value for psi at the cut where those two things meet. So in the development in D, it gives rise to a unique solution with a Taylor expansion like before. And as a consequence, what can we say is that under the same assumptions, we actually have an expansion. So looking at the first part without the remainder, that doesn't contain logarithmic divergences. So before I was saying that you could write down the tau dependence of these coefficients explicitly using Jacobi ODEs. And what you can conclude is that there's no logarithmic divergences. In fact, these coefficients are actually analytic in tau. And in particular, our tau equals plus or minus 1 and near rho equals 0, where the true degeneracies would have appeared. But here it doesn't happen. So I guess the question that I like to ask the audience when I give the talk is, were you paying attention? This is the kind of thing about, initially I spoke about polyhomogeneity, but now in fact you show that you have something actually much nicer. So that's precisely it. So you can still obtain a nice class of solutions, which actually peel in physical coordinates on the non-compact manifold under the assumptions in theorem 1. And you only see this by digging into the solutions of the Jacobi ODEs. To have well-defined solutions, you actually need the vanishing of some particular constants. And that's due to where spatial infinity in Friedrich's representation, where spatial infinity meets partial infinity. So this set called the parscriptive set, it's where the initial data you give for the Jacobi ODEs has to be nice enough for well-defined solutions, and that means you kill any logarithms which would have appeared. And maybe one other comment about the no incoming radiation condition that a few people have studied, I guess as far back as Sinfield, Manson, that under the assumptions of theorem 1, so the big horrible one, you actually have the following. So if you wanted to rewrite the no incoming radiation condition, so this is something like the rescaled field. So here I am writing phi, so this is on the unphysical spacetime. If you wanted to put this back into physical space, you multiply by a factor of r. And you want to talk about some derivative of this at partial infinity. So it's like if you're talking about Bondi coordinates or something, what you would write as v, a partial derivative of v of the rescaled field has to be 0. And in Friedrich's coordinates, this is saying a rho derivative has to vanish. And in terms of these coefficients, all that means is that at square minus, they'll be independent of rho, if that's the case, and independent of tau. And that will only depend on the angles that you give. So these are just some angular functions. And due to that, if you want the theorem to work, you actually have a no incoming radiation condition kind of built in. This is not as general as maybe like Kadar and Kerberger from earlier this year in January, but this is because we're looking at different asymptotics. Instead of polyhomogeneity, we're looking at like nice solutions or smooth solutions. Okay. Or if I wanted to rewrite that in physical coordinates, what does it actually look like? So this is what I was saying. If I give you tau and rho, but I actually rewrite this using the physical r and a Bondi coordinate u, then at the future, the physical field looks something like this. So you should recognize some of these terms, or at least the order up to which you could expand. And then you have to take a look at what's going on with these curly phi with the tilde and phi without the tilde. So the way that you can understand why we split them up is because if you were going to have solutions which contain logarithms, they would have come from the terms which contain a tilde. You can show that any of these terms actually contain no logs, but these terms would have contained logs. But in fact, the evaluation of them here at 1, so this is now u going to 1, that it doesn't contain any logarithms. So this is, I'm missing also an order of 1 over r squared term, but this is for the remainder. But what this actually tells you is that not only do you have the splitting of a regular part and a singular part in the general solution, but if you wanted actual solutions which come from your data, then what the issue is that because of this evaluation, all of the logs will actually disappear. So it's actually being able to trace why they don't appear is sort of fundamental. And maybe there's one other thing as well. So I think in December of 2024, so almost a year ago now, we had a jump scare. We thought we got scooped because I think Mark Hano and Funtanabe, they produced a paper talking about almost the exact same problem, but they weren't showing estimates. But what they showed is that through a similar study of I think they were interested more in terms of matching conditions. So where you can identify charges at future and partial infinity, where this matching condition works and where it doesn't. They considered something slightly more general for the expansions. But what they show is that, okay, by a similar study of Jacobi ODEs, but a slightly more restrictive class, I think they're ultra spherical. It just means some parameters coincide, that they actually have something which agrees in this case. Okay, so maybe, unless there's any questions so far, I'll talk about maybe just a sketch of the proof. Okay, no worries. So back to the pictures so that we can understand what's going on. So we have this setting that we want to understand. Remember that this epsilon just tells me how far down I'm pushing this hypersurface. And I split my domain into 2 regions. The analysis on this upper domain and the analysis on the lower domain. Now, one of the reasons as to why you might require so many derivatives, in one case, is that the characteristic initial value problem requires slightly more regularity. There's another thing as well, is that the way that you have to, or the way that we had used some of the tools from Friedrich, is that whatever estimate that you prove, you also have to then embed, right? You might show like Sobolev regularity, so like in these particular function spaces, and embed them into a slightly larger class to tell you something about the remainders of your expansion. So you might also have to assume some more regularity there. And there's one other thing, is that this boundary Cauchy surface, in principle, you can do something maybe slightly more refined, but what you can do is you can ensure that from the data you give on the epsilon, on a square minus, that you can get a solution up to this Cauchy surface. And in fact, what we do is we can actually, in principle, overshoot the regularity and then just restrict and then work with the previous problem that Friedrich, or at least the previous style of problem that Friedrich considered, and use an expanded version of estimates for that. So I think there's a couple of places where maybe the analysis could improve, but I think the geometry is very well placed. So let's take a look at what the higher order currents maybe actually look like, and why this approach is actually useful, and why the geometry, I think, is very well placed. So just recall, this was the first current from before, and the structures that you'll see actually make the analysis for the estimates a little bit easier. So I've written a whole mess here, but let's focus on one part at a time. So this first part, it looks like a divergence term. And this is actually why you want to use a divergence theorem. This will give you things related to the data to the boundary of your domain. So let's just consider, if I go back, let's just consider what's happening on the upper domain on N1. So the boundary contribution that you get from the cylinder will actually vanish because there's a factor of rho which will appear when you use the divergence theorem, and to get to the cylinder, you evaluate rho equals 0. So that contribution vanishes. And then what you'll have is this contribution from the Cauchy surface. The part from the null hypersurface also is going to fizzle away for a similar reason. But then the part at square plus, that will remain. So that's good. Now, this mess of angular terms, which appears down here, remember these x pluses and these z's, you should just think about them as combinations of like rotation vector fields. What's happening is that there's a nice extension of almost like an integration by parts formula, but a higher order version, which Friedrich wrote right at the end of this 2003 paper. And the terms that you generate for the higher order terms are precisely of this form. I thought this was slightly miraculous, but this is one of the features of the setup. So when you actually integrate and sum over the p, the q, and the alpha, the order of the derivative that you want, these will vanish, which is part of the analysis, which makes this pretty simple. And then these last parts here, these will produce bulk terms, and this is where you'll have some kind of estimate saying that I want my bulk terms to be controlled in terms of the initial data, so terms coming from here. And what that means is that I need these coefficients at the front to have the correct sign. So you would move them to the other side, and you would hope they have the correct sign to tell you something about the control of these components in terms of the initial data, but they have to have good sign. So the reason that crops up is because nothing I've said about P and Q have told you anything about what particular values you might choose. But this is precisely where you have a restriction on what values of P and Q, or powers of the rho derivatives and the tau derivatives that you actually need to make things work for the estimates. So maybe this is where one of the technical parts comes in, and why it might extend the number of derivatives that you need. So in fact, what happens is, once you run the energy estimates, so doing precisely what we spoke about before, that you can have, for instance, P rho derivatives of any one of your auxiliary variables. So this is the psi 0, psi 1, or psi 2. They belong to some particular Sobolev space. Then you embed them into a Holder space, and you will lose 3 derivatives. And you do that because you want to make some statement about the remainder and if this is controlled or not. That way the Taylor expansion is valid. So what that looks like is that for any of the auxiliary variables, you actually need to restrict the choice of your P to be greater than the M, the expansion order that you want, plus 1. That just guarantees good sign in the estimates. And in particular, that just means that, okay, if I want these components to lie in a sufficiently high regularity Sobolev space and then embed, you just have some technical restrictions on the P or the M in terms of R. So that's all that's going on here. If I want these derivatives to lie in a Sobolev space of a particular order, then I need to restrict my choice of P to be greater than M plus 1, or with Sobolev embedding greater than or equal to the R plus 4, which just comes from the embedding theorem. So when you take this with the restrictions that you might have on the lower domain, that's where a buildup of required regularity can come in. So that's maybe one of the technical restrictions, which you can probably alleviate doing something else. But the fundamental reason as to having smooth solutions wouldn't change doing this. even if you did something slightly more sophisticated here. So some information about future directions. I think it would be interesting to me that if you had this similar scattering result on some kind of black hole background to see what effects the curvature has on the estimates that we have to prove such a result. So this would connect more to the work of Hamad Masood and Kerberger. So, Kerberger has this lovely series of papers on the case against smooth null infinity. And Hamad Masood, he's done some like linearized scattering in Schwarzschild using a slightly different setup. And what's interesting is that the effects that curvature would have on the estimates that we've used would creep in only after the setup of this symmetric hyperbolic system. So what's interesting is that that symmetric hyperbolic system actually only relies on a congruence of time-like vectors in the region that you care about, but that's completely independent of the curvature assumption there. What would happen is that the way that you would close the estimates would be a little messier for the analysis. And I think interestingly is that the derivatives that are used in these papers are similar classes of derivatives that we use as well. And what do I mean by this? Remember when we were commuting with these higher order derivatives to make some statements about when the estimates hold, it's almost as if both us and I guess Hamad and Kerberger are using derivatives which look like, so say that you've got a v, which is your boundary coordinate at scry, at a u, which is your boundary coordinate at scry at the future. Then the derivative operators that you would end up writing would look like something like u squared partial u instead of like a partial tau or partial rho. Now, those things, when you measure regularity with respect to those derivatives, that's maybe slightly too coarse in the way that you're measuring the regularity. And you should instead, they say hindsight is 2020, and I only know this now, that you should instead use derivatives and measure derivatives with respect to the regularity, like u partial u. Now, the reason that crops up is maybe the following, is that if you want to see how the conclusions of the theorem change, you might ask if you can give sufficiently smooth data, which gives rise to polyhomogeneous behavior. And that's maybe one question you might want to answer. But then you can also say, what were the setup of the tools restricted from the beginning? So here is a nice paper of Mariam saying, if you compare different geometric blocks, maybe it doesn't matter so much. But then I think the analytic tools could be changed. And that's precisely what Juan and I are working on with Edgar. So, take now Friedrich's setting of the cylinder, but now change the analytic tools you're using. So that's where precisely the B calculus crops up. So that's where you're measuring with regularity like u partial u rather than u squared partial u at the future. That's where you might be able to capture the polyhomogeneous behavior and maybe do something slightly more sophisticated in the meantime. So we're working on starting from Cauchy data. Can you tell something about polyhomogeneous behavior? And hopefully we'll be able to produce that early next year. Depends on how hard we work. And then afterwards, kind of hinging on this result, I'll talk about the full scattering case for data at partial infinity, which isn't necessarily super smooth, and see what kind of statements you can make about the expansions that you have at future non-infinity. The analytic tools are slightly different, and will rely on a function transform, like the Mellin transform, rather than looking at particular solutions of special ordinary differential equations like the Jacobi ODE. This is ongoing work, of course, so there are lots of preliminary things to talk about, and hopefully I'll speak about this in Vienna, where I hope to see many of you, which will be very, very nice. And we'll hopefully release this paper from Overleaf Prison, maybe at the end of January or something like this. Here's some references. I'm happy to share the slides at the end. Thank you for listening. Do you have any questions?